Ladies and gentlemen, eyes up. All bets are off now. This is Count It In. How many ways can 6 different video game cartridges be arranged on a shelf if 3 must be placed beside each other? That would mean strictly there are 3 different cartridges that should be placed beside each other. Now, to answer this kind of problem, we're going to use here the concept of the fundamental counting principle that may lead to later factorial notation concepts. Now, I might say here some things that might be new to you because this is just related to the previous video. I would like you to review the previous video of the same situation, but strictly only a pair or 2 out of 6 must be placed beside each other. Using that concept, we're going to look into the possibilities for this given item. As mentioned, there are 6 different cartridges and they must be placed on a shelf. That would mean entirely the shelf has 6 different placements, okay? Because you can place here your cartridge 1, 2, 3, 4, 5, and 6, or if we're going to use colors, we have red, blue, yellow, green, orange, and purple. You can simply arrange them in any way you want. But for this situation, obviously, this is no repetition because once you place here your red cartridge, it cannot be used or it can be placed on another placement because it was already placed on our first placement here. So this is obviously with no repetition. So we are going to use here this following concepts. We used this before. We have 6 possible placements here, meaning all the 6 cartridges can be placed here. But once you place here a certain cartridge, it cannot be placed on the rest. Hence, for the next placement, only 5 possibilities occur. Same thing will happen once you use the 2 cartridges here. There are only 4 possibilities here, following with 3, 2, and 1. But this situation is for those that situation where there's no restriction like 3 must be placed beside each other, because you can guarantee here that if you use here blue, yellow, and green, since there's no restriction, you can place them anywhere you want. But here, as mentioned, the 3 must be placed beside each other. So here comes the concept. We are going to take all these 3 as 1. Okay? That would mean instead of 6 placements, now we only have 4 placements. So 1, 2, 3. The 4th placement is where strictly those 3 should go with each other. If we would like them to be placed on the first placement, again, because the 3 of them must be placed beside each other, it's also counted as 1 with the remaining 3 different placements where you are not restricted whatever cartridge you place here, as long as it's not one of those 3 that strictly must be placed beside each other. It's also true if you have your first placement here, then the group of 3, 1, 2, 3, and then your last remaining 2. So as mentioned, we will have 4 different placements now instead of 6 because 3 of those 6 placements are strictly beside each other. So this would mean that for the first placement now, there could only be 4 possible cartridges that can be used instead of 6, because as mentioned, if you have here blue, yellow, and green, okay, the possibilities that can be placed here would be the red, orange, purple, and the group of 3. So there are 4 possibilities for the first placement. For the second placement, since you will use here either red, orange, purple, or the group of 3, there are only 3 possibilities here. And once you use that for the remaining placement of those outside, those 3 placements that strictly should be together, you will have here 2 placements here. So you have 4 times 3 times 2, because this is without repetition. The 6 cartridges, or the remaining 3, can no longer be placed on the next few placements. Now, what will happen to these placements here? Because fundamental counting principle allows us to multiply all the possibilities per placement. Take note, this is just one placement now. Okay? This is similar to here, one placement and one placement. So we have 4 times 3 times 2 times 1. Regardless of that 1 is the group of 3 or 1 is any other cartridge where you use the group of 3 in either the first or second or third. But this is not yet over, because if we talk about this group of 3 alone, say for example you use here red, orange, and purple. Yes, you will have blue, yellow, and green, the group of 3 that must be placed beside each other. There is another placement if you will have yellow, blue, and green, right? Because this is another arrangement. Red, orange, purple, blue, yellow, green. Since all these 3 must be placed beside each other, you will also have red, orange, purple, yellow, blue, and green. Aside from that, you could even have blue, green, and yellow. In short, you are going to have another factor here of the number of possibilities for the specific group of 3 alone. So you would understand this by taking into consideration that this group is counted as 1, and you can rearrange them in any way you want per arrangement that you could have here. Because if you're going to have ROP or RPO, we have another set of items here. But how many arrangements do we have for the group of 3? We are going to use a separate fundamental counting principle here. So for the first placement, there are 3 possibilities because you can use the blue, yellow, or green. Once you use blue, for the second, since blue cannot be used or reused here, you will only have 2 other options. We have the yellow and green. That would mean you will have here 1 for the last. So after this, for 4 times 3 times 2 times 1, where it is originally the 6 placements where you only have 4 as you take 3 that must be placed beside each other, you have to multiply this to another fundamental counting principle of the group of 3, which is 3 times 2 times 1. Now, similar to the previous video where there's only 2 of them that must be placed beside each other, this might not be comfortable to be used if we talk about different kinds of situations. So we're going to use here the factorial notation to generalize this process. And here's the first process. This 4 times 3 times 2 times 1 can be written as 4 factorial. This stands for the 4 placements from original 6 placements where you consider the 3 of them as 1. So you have 1, 2, 3, 4. Just like this. 1, 2, 3, 4. 1, 2, 3, 4. Hence, 4 factorial. This corresponds to the number of placements that is a new number of placements once you consider the restriction. Then you multiply that to another factorial which corresponds to the number of possibilities for the grouping that you were able to consider. Hence here, 3 factorial. Why 3 factorial? Because there are 3 cartridges that must be placed beside each other. Again, this 4 factorial is the number of placements after your consideration of the restriction, and this 3 here is the number of arrangement on the restriction itself. So if you have this, you have 4 times 3 times 2 times 1. That's actually 24. So I hope I still have space here. That's 24 times your 3 factorial, which is 3 times 2 times 1, which is just 6. In short, the total number of arrangements for the 6 cartridges that must be arranged on a shelf where a restriction given to us that 3 of them must be placed beside each other is the result when we multiply 24, which is the 4 factorial, the number of arrangements considering 3 of them as 1, times 6, which is the number of arrangements that you can do on the restriction or the grouping of 3 itself. So you have here 144 arrangements. Now this is the answer for this kind of situation. And this is for candidate. Talking about getting the luck of the draw. For all in, subscribe now.